This video will be explaining Chapter 2, which is describing location in a distribution. Standardized values allow us to compare different data sets on a common scale. So, for example, SAT and ACT scores, and a z-score is an example of a standardized value, and that is how many standard deviations a value is above or below the mean. And the equation for that, which we should all have nailed down by now, is z equals x minus mu over sigma, which is x minus the mean over standard deviation. And then if we talk a little bit about percentiles, the pth percentile is the value with p% of the observations that are less than or equal to it. For example, if I were to say Caroline Arcari is in the 76th percentile for women's heights, that would mean that 76% of all women have the same or lower height than Caroline. Now we're going to do an example of a z-score. So let's say you go into your math SAT and you're feeling really good, and then you get your scores back and it says that math SAT scores have a mean of 500 and a standard deviation of 100, but you totally rocked it that day and you got a 750. So now we're going to calculate your z-score. So 750 is the x value minus 500, which is the mean, over the standard deviation, which is 100. That would be 250 over 100. So the z-score for your test is 2.5, which this means that you scored 2.5 standard deviations above the mean, which means that you did really well compared to everybody else. Density curves describe the overall pattern or shape of a distribution. They're an approximation. They're always on or above the x-axis, which means a positive. The area underneath is always equal to 1. And so the median in a density curve is when there's equal area on either side, it cuts the graph into two equal parts, and the median is resistant to outliers or skew, while the mean is when there's equal weight on either side, meaning that it's the point where the curve would balance, and it is non-resistant to outliers or skew. Here we have 4 different types of density curves. The first one up here is left skewed because we can see that the tail is more concentrated on the left, and in a skewed curve, the mean is pulled toward the tail. So you can see here that the mean is to the left of the median, and this is left skewed. Then down here, we have a symmetric bell-shaped density curve, and when it is symmetric, the mean is equal to the median. So that is up top right, you may be like, that's not a curve, but as we know, density curves don't always have to be literal curves. This is a uniform distribution. Then down here, it is right skewed because the tail is pulled to the right, and the mean is pulled toward the tail, so the mean is on the right side of the median. What's the difference between a parameter and a statistic, you might ask? A parameter describes a population, and it's usually Greek alphabet letter. An example is mu and sigma, and then a statistic describes a sample, and it's usually an English alphabet letter, and an example is x bar and s. Now for normal distributions. Normal distributions are always symmetric, unimodal, meaning there's one single peak, and bell-shaped, and they are described by the mean and the standard deviation, and this is how you write out the distribution. In a normal distribution, the mean is always equal to the median, and it's located at the center right below the peak. But be warned, not every symmetrical distribution is normal. Does everybody remember the empirical rule? Say it with me now. 68, 95, 99.7. Yay! This just means that 68% of all the data falls within one standard deviation of the mean. 95% of all the data falls within two standard deviations of the mean, and 99.7% of the data falls within three standard deviations of the mean. To check for outliers, if it's outside two standard deviations of the data, then it's definitely an outlier. And if it's outside three standard deviations, then it's an extreme outlier. These are normal distribution calculation steps. Now, to find a percent probability or area, first you state the problem in terms of x and draw your curve. Then you standardize. Then third, you use the pink packet. And lastly, you write the conclusion in context. Then to find a value, first you again state the problem in terms of x and draw a picture. Then use the pink packet, unstandardize, and finally write the conclusion in context. I'm going to try out some examples. First, what percent of observations of a standard normal variable z are greater than 2.63? So first, you're going to draw out your curve. Obviously, the mean is 0 and the standard deviation is 1. And then you're going to plot the 2.63 because it's already been standardized. And then shade above because you want to find the values greater than. Next, you're going to have to go to your pink packet, and to find 2.63, you go here, 2.6, and 3. And the value for that is 0.9957, but as we know, this value is for the probability of it being below 2.63, so you would do 100 minus 99.57, which equals 0.43. So 0.43% of the observations of a standard normal variable z are greater than 2.63. And since ain't nobody got time to flip through the pink packet and do out all those calculations, here are the calculator functions. For finding percent probability or area, you use normal CDF, left bound, right bound, mean, standard deviation. Then to find a value, you do aimed norm, percent below, mean, standard deviation.